Okay, everybody, welcome to class. Happy Monday. We finished our chapter 7 last time. Let me turn that up. We finished chapter 7 last time, and we ended talking about Weibel modulus. If we have time, we'll go back and do a few more examples of that today. We'll see how far we get today. We're going to try and cover roughly the first half of chapter 8, though. So our learning objectives, chapter 8 is all about deformation, right? Materials actually bend and deform, and this gets into the mechanisms that make that possible. So we're going to talk about plastic deformation, and first relate that to dislocation motion. That's the most important thing, right? We'll talk about the dislocation strain fields and how these relate to one another, and how that relates to things like cold working of metals, also things like recovery and recrystallization. So those, we'll define what those terms are, these basically blacksmith terms, and we'll explain how they work. We're going to introduce slip systems as a means of dislocation and actually calculate it for a single crystal. We'll have to introduce the idea of a critical resolve stress to do that. And at the end, we'll probably even talk about twinning, although that's probably going to be next class because we've got a cool demo for it. So to start with, I have a question for you, which is, how should we learn about deformation mechanisms? Should we do it via Thor's hammer, Mjolnir, or Jon Snow's sword, Longclaw? This is the most important decision you'll make today.
You misspelled Jon Snow.
Did I really? Hey, I listened to the audiobook. I never actually saw it spelled out. I don't know how you spell his name. Okay, get your answers in. I'm going to close the poll. It's going slow? It's good? Okay. If you're just coming in, make a quick frantic scramble and type in A or B. There's no right, well, there's a right answer, but I will give you points for whichever one you put in. Okay, we're going to close the poll momentarily. All right, what do people think? Yep. Like the 6 years I've been doing this, only once did they pick Jon Snow's sword. This was the closest it's got since then. It's too soon after season 8. People are still sad about it. I get it. Okay? What I love about the whole blacksmithing concept is that if you were to ask that guy, oh, so you heat it up, why did you do that? And he'll just say, because that's what the person who taught me told me how to do it, right? By trial and error over thousands of years, we figured out how to do blacksmithing just by figuring out, oh, and we don't have a cover gas when we weld, you get a really crappy weld. And oh, and I tried to bend this thing without heating it up and it just broke. Or like I tried to carve this in my hand, it was much harder. So a lot of this is like learned over time, but it's not as if they understand the material science going on in every one of those steps. And if you go to something where they like temper swords and they quench them at all these different rates of quenching, that's all material science. And again, blacksmiths have no idea the scientific reason why they do it. They just know what works and what doesn't work. And in this class, we're going to dive into the science of why do they do these different steps, okay? So let's start with deformation of metals, right? So we've said that plastic deformation, that's when you cross over from elastic to plastic. That's when you're getting permanent deformation. So this is non-recoverable deformation. One of the easiest ways to picture why this happened is motion of dislocations, okay? So take this sample here, and it's exposed to the same shear stresses at first, right? So you've got these bands going, basically smearing this material out like that, right? It's causing it to slide. In one case, you have what type of dislocation? That's a screw dislocation, right? It looks like a parking garage. In this side, you have an edge dislocation. There's an extra half row of atoms tucked in up there. It doesn't matter which type of dislocation you have. Under the exact same loading, both of these dislocations can move. This one's going to move that way, This one's going to move that way. So they move different directions, but the end result is the same deformation. Under both scenarios, even though the dislocations move different directions, you get the same final product, and it's a deformation. You literally shifted some of your atoms over. And so this is the first thing to realize with deformation is that if you have dislocations, they're going to allow you to get deformation. Okay? Deformation is very easily accomplished by the movement of these dislocations through your material. Okay? We call that slip. When dislocations move through the material, like this one here, you can see the extra half row of atoms right there. Then it's moved to here. Then it's moved to here. And finally, it pops out at the end. As it moves along a certain direction, we call the motion of dislocation slip, because they're sort of slipping through the lattice, right? The plane on which it happens, we call the slip plane. Okay? Now, as a blacksmith takes his hammer and starts pounding on a metal to deform it, or it puts in the power forge to deform it, you're going to form more and more of these dislocations. Because every time you smack that thing, you're forcing whole big sections of atoms to slide past one another. And that's going to create dislocations of all sorts of different types. So you can get really high, what are called dislocation densities. For example, in metals, they can be maybe as low as 1,000 per square millimeter. Now, why is this done per square millimeter? Because when you look at this, if you were to chop the material open and polish it, you would see the dislocations sitting along the surface. So you count them per area, right? So the dislocations, you could have 1,000 per square area, right, a square millimeter area, up to as high as like 1 billion. So you can have a huge variation in the number of dislocations and imperfections in the lattice, okay? Now, we remember, and then these numbers are much smaller for ceramics, as we'll talk about in a bit. Dislocations, if you remember, they have strain fields associated with them. If you remember, we said that this extra half row of atoms, if we draw the strain field around it, right? New version of OneNote comes with a rainbow pencil, apparently, right? You've got this region above it and below it, which have very different environments. Below it versus above it, up above it's under compression, but down below it it's under tension, right? But the point is, everywhere that you've got a dislocation, you have these strain fields around it. Those strain fields are going to react with one another. They're going to interact with one another, okay? We can see that right here. Let's say you have two dislocations of what we call the same sign. The same sign means that the extra half row of atoms on the top side in both of those scenarios. So here they're showing it in red and blue, the compression and tension, right? And if you were to bring those two things together, then you get massive compression and massive tension, right? It exacerbates the problem of strain fields. So they're not going to ever come together like that because it makes it worse. Instead, dislocations of the same sign are going to be repelled by one another, right? They're going to push each other away. And dislocations of opposite sign, if this thing was switched, they would come together and they would annihilate, right? This extra half row would meet that extra half row and it'd just become a perfect lattice, okay? So they're attracted to one another. If you have a material with 1 billion dislocations per square millimeter, what's the net result? Are they attracted to one another or repelled from one another? The net result is they're actually repelled from one another. So the more dislocations you have, the more that they don't want to be around one another. Or in other words, as you're blacksmith hammering something, has anybody done blacksmithing before? I know our 2010 students have. As you were pounding on it, did it get easier to deform or harder to deform the more you hit it? Now, part of that's because it's cooling down and you're taking away thermal energy, which doesn't let things slide past one another. But part of it is also because you're filling it with dislocations. So you're adding all these dislocations to it while you pound on it. As you add dislocations, each new dislocation moving through it, which is how you get deformation, gets harder and harder and harder, right? And so you have to, you get what's called work hardening. If anybody has done like CNC milling, some materials like Inconel, if anybody done CNC milling or anything? You can't really CNC Inconel very easily because it work hardens so much that each time you pass it over with the little blade to cut a section out, the layer underneath it gets harder and harder and harder. And you're going to break a bunch of your dies and your bits basically trying to cut that stuff because it gets so hard. So that's what work hardening is. Blacksmiths avoid this by taking it and putting it back in the furnace. Every couple, they'll do maybe 10 hammer strokes, put it back in the furnace. This does something to the dislocation density. It can change it. It goes from maybe 1 billion back down to a smaller number. You get rid of dislocations. So somebody explained to me, why on earth would dislocations go down when you put it back in the furnace? Why do we get rid of dislocations? Yeah. Yeah. You give it thermal energy, so the atoms are allowed to shift a little bit. And if they had their druthers, they would find something of the opposite side and annihilate and become a perfect lattice again. But it needs temperature for that to happen. So you have to keep on putting it back in the furnace. This is why blacksmiths are in and out of the forge constantly, because if you just kept on hammering on it, not only does it get harder and harder, but the more dislocations piling up you get in your material, the more likely it is to fracture instead of deforming. And then you have to start over. You've ruined your piece, okay? And you can see these with these really cool videos. Back in the 50s, bubble rafts were all the rage among scientists because they didn't have the microscopes that we have today to look at materials. So they would make these interesting dislocations and stuff. Like you can see there's an extra half row of atoms there just because there's a spacing that forms there. And as they poke this thing and cause another one to come by, there you had two dislocations turning into a third, right? You saw one come together with another one. Here's another one. Okay, here's a bunch of these things, right? Here you've got a bunch of dislocations, and you can see that the extra white region is all on the same side. So these are all dislocations of the same sign. So think what should happen. What do you think should happen here? Right? First off, they've got two that are almost on the same plane. They're off by one lattice plane, but they're close to one another. And then these ones are stacked up. Somebody explain to me with strain fields what's going on here. Anybody? What's happening here? Well, we said above it and below it you have opposite signs, right? So let's say that this is tension. So that's tension, 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 and tension. And then on the other side it's compression. I think I've got it backwards, but regardless. Well, look at that. I just took a tension and a compression region and I lined them up, right? That's exactly what we want. If you've got a region that's being crowded and another one's being pulled apart, when you bring those in proximity to one another, it's overall lowering the net strain on the system. So dislocations will stack up like this, and then watch what happens here. When they poke it, so they're going to mess with it. They like poke this bubble raft, this series of tiny little bubbles floating on a liquid, and when they do it, they're going to move one away. So he's just showing these two dislocations that are the same sign, almost on the same plane. Now he's going to drag it and move it away, but it's applying a stress to this. And sure enough, these things line right up. Right? On their own. They have an energetic reason why they would want to line up like that. The same thing happens in our materials, right? One last one I think we've got. Okay, an impurity. Okay. So at this point in the video, check this out. Now you've got an impurity. Wait for it. Okay, so see that bubble? It's slightly not the same size as others around. It's a little bit too big, it looks like. So they somehow created a bubble that was a little bit too big. Now watch what happens when a dislocation comes in the vicinity of that. What's in the vicinity in terms of a strain field of a too big of bubble? It's under compression. So what side of the dislocation is going to want to interact with it? It's going to be pushing away the compressive side and attracting the tensile side. So one of these dislocations comes, and watch what happens. As it comes, it pins it, right? On either side, the tension region of two different dislocations are pointing towards that impurity because overall, they have these tensile regions that they'd like to fix in the lattice, and you've got an extra big atom, so it's going to sit right between those. Why I bring this up is because impurities in metals act as dislocation pins. They pin them down. It's not that they can't leave, but they don't want to because they're at a lower energy state where they're at right now. You have to really push it to get it to leave that impurity now. So if you've got a material like sterling silver, remember what is sterling silver? It's mostly silver with 8% copper. Then you've got a bunch of impurity sites, right? Those coppers are either too big or too small for the silver lattice. I don't remember which, but it doesn't matter. Because when a dislocation comes nearby, it's going to want to stay by that because it's going to be net reduction. So if that dislocation stays where the copper atom is, instead of keeping on moving through, did you make your material harder or softer? Yeah, you made it harder. If the dislocation can't move through your material, then you don't get dislocation, or deformation, excuse me. So you made it a harder material. Sterling silver, they make sterling silver, even though copper is a cheap material, sterling silver is a better alloy because it doesn't scratch as easy, right? You replace some of the expensive silver, which is nice, and you add something that strengthens material so it doesn't scratch as easy, and it's because dislocation pinning. Okay? All right. So again, you can see that these things would line up, and you can see them. You can see bands of dislocations lined up in an actual material. If you make a material, you polish it, and then you etch it, you can see bands of dislocations lining up in a material, and average separation distances as well. They tend to be approximate average separation distances. Okay? Any questions so far on the strain fields associated with dislocations and how they move? Make sense so far? Yeah, Isaac?
Lower energy for two dislocations that aren't quite on the same plane, but like one shifted away to form a vacancy.
So are they opposite or the same sign?
They are opposite signs.
So opposite signs means they'd like to come together and combine, but you're saying there's one layer in between them. Okay, that compared to what?
It would be likely for them to come together and form a vacancy there.
Oh, would they form a vacancy if they came close together? So you're talking about, you've got this extra half row of atom here. I'm going to drop that color. That makes me kind of crazy. So you had this extra half row there, like that, but you had the same thing happening on the other side. So would they create a vacancy here? No. You'd probably get an atom diffusing there to fill that vacancy, because as soon as you put one more atom here, as you fill that spot, then you have a perfect lattice again. All that strain can be relieved if you just get an atom there. Right now it has basically a vacancy there. Oh, it would have to diffuse there. So we clearly saw how dislocations can move. It's slip, right? But atoms can also move in lattices. We'll get to that next chapter in diffusion. We're almost there. Yeah. Question?
Can you re-explain why there's like a compressive and a tensive side?
Yeah, tensile. So let's go back to our picture up here. I'm going to just zoom in on this. Atoms want to have an average separation. You can see that their average separation is maybe like that. But when you cram an extra half row of atoms in there, these things are closer than they wanted to be. Therefore, on top of this, where the extra half row is, that region of the lattice is under tensile stress. And basically, it's most intense right at the point of the dislocation, and it gets relieved the further away you go. Or in other words, inches away in the material, you don't see the strain of that thing. It's resolved. But in the near vicinity of it, you see that strain pretty acutely. Now, on the bottom side, you got the exact opposite. Instead of being the nice separation condition they want, they're more spread out here. They're a little more spread out, and so it's under tension. That's what I'm talking about there. Make sense? How do I go back to... Okay. Any other questions before we keep going? Okay, so slip, I hope I've convinced you that dislocations are important, that they interact with one another, that they can move through the lattice. So now we need to quantify how well can they move through the lattice. Is it really easy? Is it just okay easy? Is it hard? It depends on what we call the slip systems available, okay? And not all materials are the same, okay? In a slip system, that consists of both a slip plane. Remember, if this was our dislocation moving horizontally, it's happening along that plane. And then in that plane, it's going to move a certain direction, this way as opposed to that way, for example. So a slip system is a combination of a slip plane and a slip direction. This is, again, one of the reasons why we went through all the trouble of learning about planes and directions earlier this semester, so they become useful here. Now, a favorable slip system is going to minimize distortion of atoms during motion. So what do we mean motion? Again, that's back up to this point. As this extra half row of atoms slipped its way through the material, right, as this thing's moving through, it's technically distorting and moving, breaking bonds a little bit. So whichever slip system distorts it the least is going to be the most favorable one. Okay? How do we determine that? It's going to be the one that has the highest planar density. The slip plane will be the plane in your material that has the most atoms, like the highest number of density packed atoms on that plane. Because if they're packed really densely together, then it's not going to have to move very far breaking a bond before it finds another one. Okay? And then the direction where slip happens will be the most highly packed direction with the highest linear density. Right? Everybody with me? Highest planar density, highest linear density will give us slip, the most favorable slip. Slip can happen in all sorts of directions, but it's going to happen preferentially on the ones that cost the least amount of energy. So let's draw our lattice for a minute, and let's go over this. So let's draw a nice cubic lattice. We're going to draw FCC. Okay. In the FCC lattice, let's remember where our atoms are located at. They're on the corners. And they're also located on the faces, so left right, top, bottom, front, back. Okay? Now you guys tell me, what is the most densely packed plane in this structure? The most densely packed plane. Is it obvious? One of the faces is a good guess. That's not the most densely packed. Yeah?
Would it be the 1-1-1 plan?
It is the 1-1-1. What does the 1-1 look like?
The three corners that make the smallest pyramid.
Yeah, we could draw it. We'd pick an origin. Let's go through the exercise again. If I wanted you to draw the 1-1-1 plane, let's pick this as our origin. That's typically the one we want to do. 1-1-1, if that's the plane, right? 1-1-1 plane. How do we draw it? First we take the reciprocal, and it's still 1-1-1. And that means that it intersects the x, the y, and the z axes at 1. So it's going to intersect right here, here, and here. So if we draw that, it's that plane. Or if we looked at that plane over here drawn out, it has atoms at the corners, but it also has atoms along these faces. That's a pretty densely packed plane. You can't find anything more dense, close packed than that one, the 1-1-1 plane, okay? Now what's the highest density direction in this plane? The highest linear density. Would it be going right through here? No, that's not highest density. That only intersects two atoms. Well, yeah, two atoms on that distance. Instead, it's going to be along these edges, right? Going this way or that way, going this way or that way, this way or that way. Along those edges are the highest linear density direction on the highest packed plane. Or in other words, slipping along these pink lines as I've drawn them, these are where we're going to get slip in this system. Okay? Because again, when you do slip, if you slide along there, you do distort the lattice. Like as this thing gets slid over to that position, it's going to have to push other atoms out of the way. But because it's the highest density and highest linear density, it's going to push them out of the way the least. Okay? Now the next question is, how many are there? Jaden, question?
I was just going to ask, so in this structure here, the most likely plane it'll slip across is that triangle, and it'll slip in one of the directions of the edge?
Yep, that's right. His question was, it'll slip along that triangle and along one of the edge directions. That's right. That defines our slip system. We have a plane and we have directions. And those we would say are all equivalent. These are all equally good options for it to slip along. Are there other things that we're missing in this crystal structure? Are there other ones? Or in other words, what's the total number of slip systems in this? We're going to count positive and negative directions, so going this way versus that way is the same thing. That all counts as one slip system member, right? How many are there in a cubic system like FCC? So that's our next clicker question. So take a stab at that. One second. Let me go back to the right one. Oh, I didn't have it. My bad. I'll come back to that. Okay, so which one would it be? If you look at it, you start double counting. We know that there are lots of these triangular planes in this lattice. There's 8 of them actually. For example, we could have drawn that triangle, but I could also just as easily draw this triangle. The one going from this front lattice. You guys see that? That's also in the 1-1-1 family of planes. It's a different member of the family. But if we did that, they share one of these directions in common. So you can't double count those, right? Or in other words, the right number of these, if you actually count them in this face-centered cubic, it's all the ones along the faces are members of the slip system. And in the cubic system, FCC, you got these 6 faces, 2 per face. So the total number of slip systems would be 12, right? You can slide along any of the face diagonals. So 12. Everybody see how we got that? Why it's not some larger number? Okay, so FCC has 12 for its slip systems. That's a large number of slip systems. Yeah, question?
Why didn't we count the other ones? Like, why did we double count those?
Because technically in the lattice, like we can define the planes however we want, but if I start pulling on this thing, there's only those 12 that are the lowest energy things to slide along. So it doesn't matter how I defined my planes, even though two planes shared the same one, like this line along the bottom is shared by multiple different slip planes, it's still the same, it's just one direction that we actually have to pull on. In the crystal, there are 12 directions that are the lowest energy to slide along. So we'd say that there are 12 slip systems here, okay? And that's a pretty high number. And this is why FCC metals are pretty ductile. Things like copper, aluminum, these are all FCC, gold. They're FCC and they can be deformed really easily because there's lots of options for atoms to slide past one another. Whereas materials like BCC, what's an example of a BCC metal? I think magnesium or something? I forget. They're not nearly as ductile though, because the number of slip systems here, there's just 8. It's along this body diagonal, and there's only 8 of those things that we can draw. So it's much less ductile. HCP, hexagonal close packed, way less. It only has, I think, 6. So it's even less ductile. So even though materials we know that HCP and FCC are structurally very similar to one another, they don't have the same mechanical properties because the number of slip systems available. Or in other words, if you have a slip system that's, let's take a hexagonal lattice. If we take a hexagonal lattice, you've got slip systems along that top and bottom plane, what's called the basal plane, but you don't have slip systems moving vertical to it. So you have great ductility in the plane, but you don't have great ductility out of plane. And so overall, it's a much less ductile metal, right? Materials that are HCP. Any questions so far on slip systems? Nothing? Yeah, question, Abby?
Are slip systems always going to be present in planes that are most densely packed?
Yeah, your slip system by definition, the way that we define it, is the highest planar density plane in the linear density direction, right? Oh, it just means that, like literally if we like take the edge length of this, each one of these edge length is root 2a, root 2 times a, and we intersect 2 atoms for every root 2a. So if you take the number of atoms, right, we hit one center of an atom, well, half of one, and another half, so there's 2 atoms, centers that we intersect. For every square root 2 of a, there's no other direction in this plane that is higher densely packed in linear direction. Like, for example, let's say we do this. This is now some different length. It's no longer root 2a, and it intersects 1 atom, half here and half there. So it has a lower linear density. We could calculate it and show it. It's going to take some trigonometry to do it, though. Yeah, Jaden?
We could isolate like a different plane and apply like the force to that plane. It would eventually slip, but these are like the most likely planes.
That's exactly right. And in actuality, slip can occur on lots of different planes, right? Just because the 111 system in the 110 direction, those families of slip systems are the most favorable, that just means that they're more likely to happen than others. Others might still happen. For example, along the face of FCC, maybe you're going to get sliding right along the like 001 direction. Some of that might happen. It's just going to be much less prevalent. It's not going to define the ductility in the way that the other slip system will. Yeah?
And I am having a hard time understanding how it can slip on that plane when it's like literally like through an atom. Like the atom's not going to slip in half. Like what exactly is slipping on that?
Let me find a good animation for you. I can put it in a link in the announcement. But don't think of like half of atoms moving. Like imagine grabbing this whole bottom row and you're sliding along that diagonal. To do that, you're going to have to push other atoms out of the way. And that's where the strain comes from. You're going to have to slightly push them out of the way. So let me come back to that.
Atoms on the plane are moving together.
Yeah, that's right. And I have a better picture when we get to ceramics, actually, later this chapter. Any other questions about this before we keep going? Okay. Now, you can get slip in single crystals, and that's the easiest way to think of it, because single crystal, you don't have grain boundaries to worry about. Or in other words, all the way through the material, the orientation through this thing, the crystal lattice, is the same orientation all the way through the material. Growing single crystals is tricky. It's doable, but it allows us to mathematically think about this in an easier way. If you remember last chapter, we said that even though you apply a force normal to this, on some imaginary plane within the material, you have a normal to that plane, and you have all sorts of directions in that plane. And because this is now tilted, even though you applied a shear normal stress, you're going to end up with a shear stress component here. Okay? You end up with a shear stress component by doing this math right here. The shear stress is going to be equal to the normal stress that you apply, multiplied by the cosine of phi times the cosine of lambda. So if you know what these angles are between the loading direction, the slip plane normal, and the slip direction, we can figure out how much resolved shear stress there is in that direction. Because when things slide past one another, it's because of shear stress, not normal. It's shear that makes them slide past one another. So we need to calculate, all right, along that red arrow there, what is the resolved shear stress along that direction? So to do that, we need to know what these angles are. How do you figure out the angles between vectors? You do the dot product, right? You would have learned about this at some point. You come down here, right? Let's say you've got vectors A and B, right? Vector A right here and vector B right there. If you want to know the angle between those, then you know that A dot B is equal to the length of A multiplied by the length of B cosine of theta, that angle. Okay? So how do you do a dot product? That's easy. You just take, if the two terms are U1, V1, W1, and U2, V2, W2, right, for the two different vectors, when you do the dot product, you take the U's and you multiply them. Then you add that to the V's multiplied together, and you add that to the W's. So this top part right here, that's our dot product up along in the numerator. Anybody not remembering dot products? That sound familiar, I hope? And then the length of a vector, how do you take the length of a vector? You just take the square root of each one of the U, V, and W's squared, added up. So right, here's the first vector, U, V, and W. You square each one of those terms, you add them up, and you take the square root. Now we're going to multiply that by the B vector. So all of a sudden, the theta, the angle theta for this is just the inverse cosine of all that vector algebra. Everybody remember how to do that? If not, the TAs can give you a primer on it. But this is pretty slick. In other words, if we know that we're pulling along the, let's say this is like the 1, 0, 0 direction, right? And we know that this is that's the 1, 1, 1 plane. The normal to that will be 1, 1, 1. And then there's some direction along there. Let's say that it's like the, I don't know, the O 1 bar 1 direction. We can do a series of dot products to figure out what the angles are between those. Now, this is important to note that what I said there, I sort of went over it quickly. I said because this is the 1, 1, 1 plane, the vector normal to it is also 1, 1, 1. That only works in the cubic system. In a non-cubic system, you have to do some gross algebra to get it, and we're not going to do that in this class. Okay? Everybody with me so far? So if I said now it's a BCC crystal, where the slip plane is no longer the 1, 1, 1, but the 1, 1, 0, the normal to it would be the 1, 1, 0, would be the normal to that slip plane. Okay? Let's do an example. Okay, let's do this question. We'll work it out together. It says, determine the tensile stress that is applied along the 110 axis of a silver crystal that will cause slip along the 111 plane in the 011 direction, right? The critical resolved shear stress is 6 megapascals. So going back to our formula, we said that the shear stress is equal to the applied normal stress multiplied by the cosine of phi times the cosine of lambda, where phi and lambda, phi was, I think that was between, well, it doesn't matter. It's between, let's say, loading direction and slip normal. And this is between the loading and the slip direction. Okay? What this problem tells you, it says that there is a critical resolved shear stress. In other words, when this tau value equals 6 megapascals, these atoms will start to slide past one another in this crystal, right? So when that equals 6 megapascals over here, we want to know the stress that you apply to it normally in order to get it to slip along those specific directions, right? So to do this, we want cosine of phi, right? So cosine of phi, by the way, take a look at this. If we just bring these things over, if we divide this by that, we don't ever actually have to take the inverse cosine, because all we're looking for is the cosine of the angle, right? That's what the formula calls for. So all we have to do is the dot product divided by the length. We don't have to turn it in. We don't have to solve for the angle, right? Because what we need is the cosine of the angle. Okay? So let's do this one. A dot B. What would A dot B be? So let's write these out. We've got 1, 1, 0 dot. The slip normal is going to be 1, 1, 1. And then this one, the loading direction is 1, 1, 0 dot 0, 1, 1. Everybody with me so far? This hopefully is familiar. Okay, so let's take the dot product of this one. 1 times 1 plus 1 times 1 plus 0 times 1. So 1 times 1 plus 1 times 1 plus 0 times 1. We're going to divide that by the length of those vectors. That's going to be the square root of 2 times the square root of 3. We're going to multiply that by, now we take the new dot product, 1 times 0 plus 1 times 1 plus 0 times 1. 0, it's backwards. 1 times 0 plus 1 times 1 plus 0 times 1. Divide that thing by the length of those vectors. The length of those vectors is square root of 2 and square root of 2. Again, if this is not familiar, come and visit me or the TAs and we'll do a primer on it. I'm going quickly through it here. Okay? So these just equal numbers. So go ahead and plug those in and tell me what the stress is that will cause this crystal to slip along that slip system. Okay, get your answers in, and then when you're done, you can take off. And we'll see you guys next class. What's that? Oh, yeah. What's that?
Are we going over the answer or are we ending it right here?
I'll probably pick up the next class. We're out of time.